Okay, so basically the first thing that I'm going to go over is exactly what a neural network is and how it works. So you'll have to bear with me with some terrible drawings, but a neural network basically is a collection of nodes, and these nodes are in layers.
Sam, your screen's not visible.
Oh, okay. That is a good point. That is a very good point. I will share my screen. Okay. So if you remember, Keshev, this was kind of, do you remember the neural network kind of looking like this?
Yeah, yep. Those are the layers of. Yeah.
Yep. Yep. Um, all right. And there's three types of layers. There's your input layer, which is this first layer, this first layer here, where all the data inputs go in. And then there's your output layer. Now, each of these output layers should have a probability of one of the classes that you. So say in this one, say I'd have 1, 2, 3, 4, 5. I have 5 different classes that I was guessing, and each one of these would have a probability and of it being this class, and these should all add up to 1. Right? Now, these are all connected. Each node is connected to each other node, like that. Can actually draw these properly. So each of these gets input from each of these, right? Now, on one of these, when the input goes in, it gets multiplied by a weight, and a bias. Right, so by the time the input leaves this neuron and goes into this neuron, it's been multiplied by a weight and a bias. And when it's in the neuron, it also has an additional function. It also has, let's call it theta, goes through an additional function. So two things will happen. It will have the weight and the bias input when it's traveling to the next neuron, and when it gets to the next neuron, it will have a function performed on it. There are several different functions. A common one is a ReLU, which is a rectified linear unit, and basically all that does is if the value is of the input is less than 0, then it will equal 0, and if it's more than 0, then it equals itself. So a graph of a ReLU just looks like this. That's the most simple function you can do. There's also softmax and sigmoid and a whole lot of others. They use exponentials. They're a bit more complicated. I'm not going into them at the moment, but that's basically what a neural network is doing. Each of these, it's having the weights and the biases added, and then it's going for a function, and then the input goes onto the next neuron, and has the same thing happen again, and it goes to the next one until it gets to the output layer, where the output layer is usually a softmax, because what a softmax function does is it normalizes, which means it puts everything between 0 and 1. I'll just show you I'll just show you what a softmax function looks like. You get an idea. See if I can find what the math looks like. Yep, this is what a softmax function looks like. So it's an exponential of it's exponential to the power of the input over the sum of exponential to the power of the other input. This makes more sense if you're looking at it as a matrix. But as you can see, they get a bit more complicated when you go into different functions other than the ReLU. How's your can I just ask Kashev, how's your understanding of like how a neural network works so far?
It's pretty lenient, but it's I'm not too far ahead, but yeah, I know how it basically just functions.
Yeah,
Yeah.
basically it looks like this. The main things to remember, it looks like this. It has layers of neurons, has input layer, a number of hidden layers in the middle, and then it has an output layer. The output layer tries to assign a probability to each of the classes, and they will add up to 1. And when the inputs move from layer to layer, they get multiplied by weights and biases. And these are the things that you update, and you try and get the most optimal weights and biases, and that's how you try and improve. That's how you improve your neural network each time it runs. And when the inputs get to a neuron, they have an additional function applied to them also. That's the major points of how a neural network
So,
operates.
to sum it up, the first layer is always the input layer, and
Yep.
what it does is it just puts up ReLU where if the value is a negative, it sums it up to a 0, and if it's a positive, it passes it on as it is,
Yep.
and that goes into the middle layers where it has another function which is applied on the input, and the output is passed down to the final layer, which is a sigmoid, which sums up the result between a range of 0 and 1.
Yep. And generally, if you're just doing a straight classifier, if you which is you'll have a list of features, which is the information that it tries to guess on, and then it has at the end it has a target variable, which is the class, which is what you're trying to guess. Do you get that?
Yeah.
Yep. So generally, the number of input in a regular flat neural network, the number of inputs will these will be the number of features. So say you've got 30 features, then you'll have 30 input neurons. Right? And the number of these output neurons will be the number of classes. Because what these are doing is they're assigning a probability of each class. So say this is red, green, blue, and yellow. It might have red as 0.3, green 0.2, blue 0.4, and yellow 0.1. So yellow 0.1, that means there's a 10% chance that the thing is yellow. Does that make sense?
Yep.
Yep. Right. So that's basically a very, very basic neural network. I'll show you what the neural network looks like in Python, actually, if I can find which one it is. So I've got one. Yeah. This is in PyTorch. You can use either PyTorch. There's two things you can use to do a neural network. You can use either PyTorch or you can use TensorFlow. They're two different Python libraries. And it's quite easy, you know, if you're trying to do a neural network, it's quite easy to just Google it and find the documentation to do a basic neural network. If you just look in the like the PyTorch, you know, like the PyTorch documentation or the TensorFlow. I've been doing mine in PyTorch. So you just need to, this stuff's all just getting the data set, getting the training, getting splitting it into train, validation, and test sets. Now this is just with a linear inputs. So the input is just like a vector with a certain number of you know, like 30 classes or whatever. Now this one only has 3 layers. It has an input layer, a hidden layer, and an output layer. You see this, the output layer, it gets 64 inputs into it from this one, and it tries to convert it into just two outputs because there's just 2 classes. So this is the breast cancer. This is the breast cancer data set, and has breast cancer and doesn't have breast cancer. So this is the number of outputs here is 2. Now what this is doing, this nn.linear, this is that bit that I said before where it does the weights. This is a linear function where it multiplies by the weights and adds the biases. This is the linear part, and this part is the function that happens in the neurons. This is the ReLU. This is this part. You have to, in PyTorch, you have to do all these manually. Generally this, once it gets to this linear layer, so this part is pertaining to these connections. All right, this part is pertaining to these connections. But generally it would have a softmax that's applied onto it in the final output layer, but that softmax in PyTorch, that's carried out automatically by the optimizer. So we don't actually need to put in a layer. We don't actually need to put in a layer to do the softmax. It's just applied by automatically by the optimizer that we use. So that's basically what a neural network model looks like in PyTorch. Now, I also need to explain again what happens once you get to the end of this neural network. If you'll get a series of predictions from each of these neurons, and from that, and you'll then compare them to the ground truth, because when we're training it, we know the ground truth labels. Like we know if something's red or green or blue or whatever. And for each prediction, we will compare the actual prediction. We'll compare the prediction we get from the model, which we call y hat, to the ground truth prediction, which we call y. And we will generally get a loss function. Now the loss function, the most basic loss function, right. Most basic loss function we can use is y hat minus y squared as basically the least sum of the least squares, y hat minus y squared on n. That's like the most basic loss function we can use. There are a lot of others. And what we've got to do now is we don't want the loss function compared to y. We want we want the rate of change of the loss, the derivative of the loss function, compared to each of the inputs, compared to x. We want to find out how much each of these inputs affects the loss. If you find out how much each of these affects the loss, we can figure out how best to change the weights and the biases to get the most accurate model that we can. So basically what we do is we get the derivative of the loss function, which in this case, the derivative. Have you done much? Do you know how to do derivatives and things? Have you done much maths?
Yep. So the square, in case of a square, the two, uh, let's say y square becomes 2 to the times of y.
Yep. Yep. So this
Yeah.
2 comes down the front, doesn't it?
Mhm.
So it'll be 2. And do you know how the chain rule works? All right, and you know that the n will just stay there because that's just multiplying this. And that'll be times. Do you know why this is 2 y hat minus y on n times 1? Do you know where the times 1 comes from?
Uh, I don't know, because into times one's always the same number. I mean,
Because it's
are you trying?
yeah, it's the chain rule because we're looking at the derivative. We're looking at the derivative of L, the loss, with respect to y with respect to this, right? Say
Okay. Okay, so we're also doing it for just the y.
yeah. So say let's
Okay.
actually cross this out. Let's say we're looking at it with respect to y hat, right? We want the gradient of a loss with respect to the prediction. So this, because we've got this square here, that's like a function of a function, right?
Okay.
So we have to find the derivative of this function with a squared sign in it, and then we have to multiply it by the derivative of this function that's inside the brackets. And the derivative of this function that's inside the
Okay.
brackets of y minus y hat is just 1, because the derivative of y hat is 1, and then this
Okay.
goes to
Yeah.
0 because it's not one of the variables.
There's no power. Yeah. Yeah. Yeah.
Yeah, yeah. All right. So that's why, and it's important to know the chain rule, because basically each of these neurons, rub some of this out. Probably easier just to start a. Wonder if I can. Do you know if I can select all these and? Yeah, I can do that. Nice. Right. Now, the way we can think of these. Hey, that's a function, right? F of x. And this will be g of f of x. This will be h of g of f of x. Do you get why I've written them like this? Like why this is f of x and this is g of f of x and this is h of g of f of x?
Yeah, because the f of x is the output that will the input layer give, which will be passed on to the
Yep,
middle layers, and
yep,
the result with which will be sent into the final layer.
Yep, perfect. So in order to get derivatives of these, we just use the chain rule. So have you heard of this one? Have you heard of dy dx equals dy dh times dh dx? All right, so this is basically the chain. This is basically the chain rule. So the derivative dy dx, the change of y with respect to the change in x, is equal to the change. If we've got like g of f of x, if we've got like two functions, then dy dx is equal to dy dh times dh dx. That's kind of what I was showing you before. Like it's the derivative of the overall of the big function, the overall derivative of a big function multiplied by the derivative of the smaller function that's within the big function. Does that make sense?
Yeah, got it, yeah.
So it's like for g of f of x, it's like for g dash f of x times f dash x. Right, so it's it's the external derivative multiplied by the internal derivative. All right, get rid of this. So basically, all we do, we start with the loss function. This is called back propagation. We start at the loss function that comes out of this final layer, and what we've got then is we've got the loss with respect to each of these outputs, right? But what we want is the loss with respect to each of these inputs, because then we can figure out how we change the inputs to minimize the loss. So we have to work back through this function and work through using the chain rule and work out the loss with respect to the gradient, the loss with respect to the values at each of these. So the first at these outputs, the first one is the loss with respect to y, with respect to each prediction with respect to y hat, and then I'll should actually try and write this. So the first one we get is the loss with respect to y hat. Now say we call this one Z, right? Say we call this value Z, and Z will be a function of y hat because of these. So we don't want this. We want the loss with respect to Z. So we can dl dz equals dl dy hat times dy hat dz. And we've already got dl dy, we've already got this part. That's this, because we worked out the derivative of a loss function first. So we've already got this part. So we just need to work out this part. Just need to work out this gradient and then multiply them. And then we get the derivative of the loss function with respect to this value. Do you understand what's going on so far?
Yeah. So basically, we are inputting chain rule so that we can calculate the loss function of the middle layers.
Yep.
instead of just
Yep,
getting it from the
yep.
last layer.
And ultimately we want dldx, which is with respect to the input. So we'll do exactly the same thing we did for Z. We'll do
Yeah,
exactly the
and do
same
it
thing
backwards.
for
Yeah.
this layer.
Okay.
And the reason we have to do it backwards is because each of these gradients informs the gradient at this node, because the gradient at this node depends on each of these inputs. So we work out the gradient of each of these with respect to Z, and then we sum them up, and that will be the value. Then that will be the value of the gradient at Z. Does that make sense?
Yeah, got it. Yeah.
Yep. And if we did it the other way, then we wouldn't be able to do it in one pass. We'd have to do heaps of passes, because we'd have to work out for this one, and then we'd have to work out for this one, and then we'd have to work out for this one. We'd have to do all of these gradients separately and then add them all up at the end. And it would take a lot longer and use a lot more computing power. By doing it backwards, we work out the gradient at each one of these, add them up, and then work out the gradient of this, and work out the gradient of each of these, add them up, and work out the gradient of this. That's why we do the back propagation. So at the end, once we've done all this, we will have the gradient with respect to the input, which is what we want. And then all we have to do is put it into our optimization function. So I've got a thing called the learning rate. And this is a hyperparameter. A hyperparameter is something that we can change to. Do you know what hyperparameters are?
Is it like a range between?
The hyperparameters are the things that we can change. They're the things like because have you done any
Okay,
machine?
yeah, got it. So the
Yeah,
number of apples or the number of, you
yeah,
know.
yeah. It's just like, for instance, we can change the number of layers, or we can change the number of neurons, stuff
Okay,
like
yeah.
that. That's called a hyperparameter, because we can just change that at will. And it's the
Okay.
same thing with this learning rate. So we'll get the learning rate times the gradient, and basically we just subtract this from the weights. We do the weights minus the learning rate times gradient. This is what's known as an optimization function. We don't have to use this exact function. This is one that's commonly used. There's a number of, I think this is called ADAM. I'm not sure. So Adam, but I'm not sure if that's the right one. But there's a number of different optimization functions. I'm not sure if this is Adam. It might be a different one, but this is like the most basic thing we can do. So, and do you understand that because we've got for each of these ones, we've got those W times X plus B. Right, so this is our weights. This W is our weights that we multiply by X, and this B is our biases. So this is a matrix. This is a matrix with, and this is a vector. Do you get why this will be a matrix and this will be a vector? Because this we're multiplying and this we're just adding.
Okay.
Yep. So both of the weights and the biases get updated by this optimization function. We also have the biases minus the learning rate times the gradient. And that's basically what we're doing each training thing is called an epoch. And basically what we're doing each time is we're first doing the forward pass, which is where we get the inputs and we multiply them by the weights and biases on these things. We do the functions on these things, and eventually we get the outputs and the predictions of the probability. We then use we then compare these predictions to the ground truth, and we get y minus y hat, which is the loss, and we get the loss function. And then we work out the gradient of the loss function with respect to the inputs, and we back propagate it through all of this. And then we use that gradient to update the weights and the biases. And then hopefully the next time we do a forward, and then we'll do it again, and we'll do another forward pass and work out new predictions. And hopefully they will be more accurate because we've worked out better weights and biases. What we're doing when we get the gradient and we subtract it, we're trying to find the minimum point. We're trying to find the point where the gradient is equal to 0, as close to that as possible, and that will be, the minimum. This is the loss function. We're trying to find the minimum point of the loss function. Right, that's what we're doing when we're getting the gradient, and we're trying to, we're subtracting it from the weights. We're trying to get to the minimum. We're trying to get to the minimum point of the loss function. How much sense does this make so far?
Pretty good so far. I mean, I get the gist of how it works, how we do by propagation,
Yeah,
and yeah, how we calculate the loss. It
you don't.
also, yeah,
You don't need an in-depth mathematical understanding of this. You just need a general idea of what's going on, because the computer does it for you, basically, all this calculation stuff. You don't need to calculate gradients and stuff like that. But it is generally better. This is the most complicated part, and it's generally better if you have an understanding of what a network is doing. So you know what's happening when you. And I mean, when you're using PyTorch, you'd have to have a bit of an understanding of it, because you have to do the training loops manually. You have to do it like this. So you have to for each epoch. Say you're training for 60 epochs, and then for this is for each input, right? For I in range, for the length for the length of the training set, for each training example. Do you know what batching is?
just taking the training data and splitting it into multiple small batches.
Yeah. What it's
Yeah.
doing basically, in a basic neural network, you would calculate one input at a time, right? You calculate one input at a time. Each of the, see if I can go back to this. Say you've got an input. 2, 5, 7, 9, 4. Say you've got an input like this, and this is all your features, right? You say you've got an input 2, 5, 7, 9, 4. So you've got 5 features, and say that's red. And what you're doing is you're using all these features to try and guess what color this input is. Does that make sense?
Yep.
Yep. All batching is, say if you've got a batch size of 2, instead of putting this vector into here and calculating and into here and calculating these one at a time, if you've got a batch size of 2, you'll calculate 2 at a time. So you'll add another. So you'll add another example. Have different things in it. And say this is yellow. So you're running this calculation when you put the, you're going to feed this in as a matrix. You're going to feed this in as a matrix rather than a vector. And you're going to calculate all this at once. So it basically just makes training faster.
Okay, yeah.
So when you think of a batch, just think of you're getting one input. Instead of getting one input, you're getting like
You're passing a matrix
4
of different,
inputs
multiple
and putting
inputs.
them in a matrix and putting them in all at once, and it just makes it process it faster. Sometimes that backfires and it makes the processing more complicated, so it can make it slower. That's why you've got to get your batch size right. But that's basically what a batch is. So for each epoch, for each
train.
for each batch that you're training, all right. Calculating your inputs and your targets, you set your optimizer to 0. You do the forward pass, right? So this is the first part. This is the first part that I was talking about, where you get your inputs and you do all these calculations on them, and then you get your outputs. That's your forward pass. Then you compute the loss. This is the loss equals this is your loss function. All right, and you compute your loss. Then you do the backward pass, which is calculating all the gradients. Then this part, optimizer.step, this is doing this, where you're subtracting the learning rate. We're subtracting the learning rate times the gradient from the weights and the biases. That's this part. And then once you get to here, you don't really need this stuff. Once you get to here, that's when you can do it again for the next epoch or for the next part of the batch. You do this for each one of the batches, and then it goes and does it for the next training epoch. This stuff is just recording the predictions and recording how many it got correct and how many it got incorrect, and working out the accuracy and stuff like that. But for it to just operate and do the forward and backward passes and update the weights, all you need is this stuff. All right, and that is basically how a neural network works. And I can give you some of this code if you want, just so you've got it for reference. If you're ever trying to create, if you're ever trying to build a network yourself, you can just look at this code, and if you've got a basic understanding of it, you can adapt it to whatever you're trying to do. Now, that's the first part. That is a basic neural network, and how you get it in Python, right? So what I'm doing with this project is actually a bit different. Let's get into a new neural network. Save that. Now what I'm doing is image classification. So instead of an input for image classification, instead of a flat input like this, for an image, obviously it's a bit different, because I've got you've got each pixel in the image, right? So that makes a matrix, because you're looking at something that does each pixel. Each pixel also has 3 channels. Have you heard of the red, blue, green channels for an image?
Yeah, how mixing different ratios of what these three colors make all
Yes.
the colors in the spectrum.
Yes. So an orange pixel might be like 30% red, 30% red, 40% yellow, and 1% blue. You know, something like that. So each of these will have 3 channels. So we've already got a 3-dimensional tensor. Do you know what a tensor is?
It's a multidimensional, right?
Yep. Basically, yeah. So we've got a 3-dimensional tensor. It'll have an additional 4th dimension for the batch size. If we've got, if we're processing not one of these, but like 5 of them at the same time, it'll have a different dimension. It'll have, that'll add an extra dimension to the tensor. And so we use a different thing. We don't just use a vanilla network model like this. We use a thing called a convolution. The main one for an image thing is the one that you were working on. It's called a convolutional neural network. Now I'll explain to you a bit how that works. I'll show you an image of a convolutional network. Because I got one before, if I can find it. All right, this is a convolutional network, and you see it's a bit more complicated than the simple structure we were looking at before, which was just for flat vector inputs. This one has 2 parts to it. Yep.
No, although I was just saying it has 3 layers. That's it.
Yep. But you see, as you can see, it looks a bit more complicated, but it's got 2 parts. This part is a thing that creates a feature map. This creates another matrix that highlights edges, corners, all sorts of features in the image. And this one is the classifier. This is more like the simple neural network we had before. It's just looking at each part. It's just looking at each part of the image and trying to classify it as one of the classes. So in our case, we've got faces, and we want to classify if a face is happy, sad, angry, etc. So this will classify this. What this will do is this will create a very large tensor that that maps edges, corners, and other features. It won't classify it. It won't give it classes. It will just point out what the features are. And once you've done that, you then go ahead and use this and run this classifier on the output on this feature map. You run this classifier, and that will tell you what class, and that will help you guess what class it is. Now, as you can see, this is very similar to this, right? This is a standard neural network classifier, which is what I explained to you in the last part, right? Does that make sense? You there?
Yeah. It
Yep.
is.
Does that make sense? This part is the same classifier that we did in the last part. Okay.
So the one on the top, what we're basically doing is we're just trying to make different batches and passing it on to the same thing you just explained. So the classifier is the only thing that matters. The features, it's like the first layer of the
Yeah,
difference.
it's 2 steps. It's a 2-step process. First, we create the feature map, the map of the features, and then we classify that map. What this feature thing is like is it will you'll have your image, right? Say this is your base image. Say it's the person, right? This is your actually we won't do that. We'll say it's a face because that's what we're actually looking
Okay.
at.
So each grin becomes an element of the matrix.
Yeah.
Okay.
So hey, this is a face. All right. This is a base image. Now what the feature map will do is it will create a number of different matrices that specifically focus on certain features. So you might have one that's specifically focusing on edges, and it will pick out, things like, I don't know, like the nose or some part of the mouth or whatever. You might have another one that's focusing on corners, so it'll pick out, like the corners of the eye or the
The dimples on the cheeks,
end of the
all this
nose or
stuff.
the
Okay.
dimples of the cheeks, yeah, stuff like that. And the feature map is a collection. It's a tensor, right? It's a tensor, so it's a collection of all these features. And then what the classifier will do is it will come along and it will classify each one of these features. So it might a corner of the eye like this, it might classify it as angry, or a nose like this, it might classify it as sad, or whatever. And that's do you kind of get the two-stage process, like getting the
Yes.
features and then classifying the features,
Yes.
and classifying them is just a regular neural network like this part. The features is a bit different. Now I'll explain to you how the features work, how it does the features as best that I can. What it will do, say we've got this matrix, and say each of these entries in the matrix is a pixel value, right? Each of these is a value of one of the pixels. So I might put some different, like that might be 1, that might be 2, might be 4. Each of these is just a direct mapping of the pixels in the image. Now, what we're doing with this thing, see, we've got several layers here. The first layer in this neural network is a convolutional layer, right? And that's, again, you know how I was saying we have different channels that map different things. So there's one that might have edges, there's one that might have corners, so it might get like the dimples of the cheeks and things like that. So
Mhm.
this will produce 16 maps of different features,
Okay.
right?
Okay.
And
Yeah.
this is just another dimension in the tensor. And what this convolutional network does is it takes a big matrix like this, that's got all the values of the pixels on it, and it will slide a smaller matrix, which is called a kernel, and it'll be a basic kernel is like 1, 1, 1, 0, 0, 0,
So
1,
one implies the feature
this
exists
one.
in the image that we pass through.
Yep. So
Okay.
this is an example of a kernel, and this is called a kernel, right? Okay. Oh. And what the kernel will do is, say there's different sorts of kernels. Say this, I think this is an edge detection kernel, right? So this is a kernel that they would use to make the output channel that that detects edges, and they run this kernel, this small matrix, this kernel, over this big matrix. So in the top left corner, the kernel will just cover over this top part of the matrix, and they will just multiply it element wise. So they'll do you know what element wise multiplication matrix multiplication is?
Yeah, I did. So
Yep,
we multiply the row with the column,
yep,
or
yep.
is it the inverse? Yeah.
Multiply each of the, yeah, multiply this by this, this by
Mm-hmm,
this, this by
mm-hmm.
this, and then sum them all up and get one number. That makes
Yes.
sense?
Yeah. Yeah.
Yep.
Yeah.
And this one number that we get in our channel, let's say this is channel 1. What? Channel 1, right? The number that we get for element-wise multiplication, this, say it's 9, this will be our first entry in our matrix. And then all we do is we slide this matrix, instead of having it here doing these numbers.
Mm-hmm.
Let's put some more numbers here. Let's do 6 and 5. Why not? Instead of doing these numbers, we'll slide it 1 to the left. So it'll be starting here on this second row, and it'll be doing these numbers, right? And we'll just do another element rise multiplication. So multiply all the numbers, sum them up, and that will be our next entry in this matrix. So this might be 4. So we're just sliding this kernel over each of these entries in this big matrix to get the values of our channel. Does that make sense?
Yes.
Right. And this channel is and each kernel will specialize in doing something. So like I said, this kernel, I'm pretty sure, is a kernel that specializes in detecting edges. So this channel will map out where all the edges are in an image. You might have another one, like I said, that detects corners. You might have one that detects gradients. There's several different features that they look for, and that's what this convolutional layer. That's all this convolutional layer is doing. It's sliding one of these kernels over this big matrix, this big image matrix, and calculating the maps of the features. Now, once we've done that, it then just goes for a real layer, and just to neaten up the values a bit. Now you can imagine, once we've done this, we've got a pretty big tensor, because we've got 16 channels, we've got 16 of these matrices for each of these these. So it's like, we're taking this and multiplying it by 16. Basically.
Okay.
So all this pooling layer is doing is it's reducing the size of the feature maps. It's basically what it does. Say if we've got 2 by 2 max pooling, it'll take a matrix like this. So we've got 8 and 6. So you've got a 2 by 2 matrix like this. It will find the maximum entry, and it will use, instead of 9486, it'll just turn this into 9. So if we've got a big feature map with heaps of stuff on it, it will only outline the most important. It will only be looking at the most
Dominating
important
one.
features.
Yeah.
So, and it basically just saves it makes computing easier. It saves calculation time, and just reduces the size of this giant tensor we get from doing this, and it just makes it easier to calculate. That's all this max pooling stuff is. So you don't need to worry too much about that. But generally, a convolutional network will have this max pooling. That's what it is, and that's why you include it, as it reduces the size. It reduces the size of this and makes it easier to compute, and it does that by taking out the most important features. Does that make sense?
Yeah. I got it.
Yep. And like I said, you don't need to understand everything. You don't need to have a really good know exactly how to calculate everything. You just need a basic understanding of how stuff works. So you know how to, if you want to go to do a convolutional neural network, you know what each of these, what to put in it, and what each of the things do. That's a convolutional neural network. So it uses the kernel and creates the maps of the features, and then it
Mhm.
goes over the features and classifies each of them. That's all it does. Now, the one that I'm using in this is the one this is a CNN. This is the one that you were looking at. That got up to 62. Now, I was actually using one that was slightly different. I was using what's called a Resnet. Now, what Resnet is, it is a convolutional neural network. This feature map has been pre-trained on a thing called ImageNet. ImageNet is a big database of images a big database of images online, and this feature map has already been pre-trained on this big database of images. So it's going to be better hopefully it will be better at bringing out the features, at classifying edges and corners and things like that. Hopefully it will be more accurate. And the other thing that it allows us to do, and this is hopefully the last complicated concept I'm going to explain to you. Have you ever heard of a thing called the vanishing gradient problem?
Uh, it's, no, I don't think so.
Um, it's actually more simple than it sounds, right? You know how we're doing. You remember how I explained the back propagation? How it's
Yeah,
just it's just it's just all these gradients. It's like
yeah, yeah, for training, yeah. Hello?
yeah. And in a big neural network, say we've got 36 layers, we're going to have 36. We're going to be multiplying 36 gradients by each other to get the derivative of L with respect to X. Because of the chain rule, we're going to be multiplying like 36 gradients.
Times
Does
two.
that make
Okay.
sense?
Yeah.
And if we're using stuff like if we're using a lot of the functions that we have in the neurons, things like a sigmoid function, um, uh, ReLU isn't actually the gradient of a ReLU is just one, but a lot of like the sigmoid function, which is a common one, the graph of a sigmoid function looks graph of a sigmoid looks like this, right? A sigmoid function is one that's commonly used in the neurons. And the maximum gradient of this thing is like 0.2, right? That's the maximum gradient of this function. Now, imagine if we have like 30 layers, each of them with one of these, and the gradient is like 0.2. Imagine if if
Keep on multiplying. Yeah.
you multiply 0.2 by 0.2 by 0.2 by 0.2, we get up, by the time we get up to the first, it's fine in the later layers,
It will be too
right?
small.
But by the time we get up to the input, by the time we get up to the input layer, we've got, we've got like 0.0002 in our gradient. And the weights in these input layers aren't going to get updated because The gradient is too small. That makes sense?
Yeah, so okay, got it. So the weights are just gonna be added up to 0.00002. So it it it's too small to make a difference.
Yeah, because it's basically the weight minus the optimization, most basic optimization, the weight minus the gradient. If our gradient is tiny, then our weights aren't going to change. That makes sense? Yep. Okay. So what the ReLU does is instead of for instead of in the thing, instead of f of x equals, instead of f of x equals a function of x, so it's instead of like f of x equals 3x, it will go f of x equals g of x plus x. So it will separate the input, and it'll have function. In this thing, in 3 of x, this g of x will equal 2 of x, because 2 of x plus x is 3 of x. So it separates an input out the front. Does that make sense?
Yeah.
At this stage, that's called a residual, right? That's called a residual if it separates it like this. And say if it's x squared, what do you think it would be if we had, if f of x was x squared? What would this residual do to it? How would we get it in the form g of x? How would we get x squared in the form of g of x plus x?
I'm guessing x square minus x plus
Yep,
x.
beautiful.
Yeah.
Yep, that's it. That's
Yeah.
it. Yeah. So that's what it's doing. It just separates the input from the instead of performing a function on the input, it adds a function to the input. That's the residual, and this is used in what's called a skip connection. How this this will make sense at the end. It probably won't make sense now, but it will make sense at the end. So say we've got these are, say we've got a neuron, say we've got a couple of neurons here, and because we separate out this x, what we can do, so this is a connection here, all right, and this, so all these things are performing functions on the x, but what we can do is we can take x out here and put it back in here. So in this part, we've got our changed thing, and we're also adding x to it. Now what this does is when we backpropagate and go for all our gradients, no matter how small the gradient of this f of x function is, the gradient of x is always going to be 1. So it's always, so say we've got like 0.002 for our f of x, it's going to be 0.002 plus 1. So we're going to, instead of these gradients going to 0, they're going to go to 1, which is, so instead of say we've got the chain rule, so the chain rule dy dx equals y d h times d h dx. Right. Now, if this is if dh dx is 0, this whole thing is this whole gradient is going to go to 0, right? But if dh dx is 1, the gradient is just going to go to dy dh. Does that make sense?
Yeah.
So the gradients at the input will just stay as the gradients at the output. So those gradients will those gradients will still get through and back proper and get to the rest of the then get to the rest of the layers. That's how Resnet uses these residual and skip connections to solve the vanishing gradient problem. And basically what that means is you can build much deeper and more complex models using using Resnet because it has this mechanism with this is called residual and skip connections. It uses this mechanism to solve the vanishing gradient problem. That's a major reason people use Resnet. That's that, and also that it's been that, and also the
Okay,
feature.
the pre-trained features here.
Yeah, and also the pre-trained features. Now I can actually explain a bit what I've done. I've also used a bit of a pipe. Which one is? It's not the one I'm looking for. I've got several. Right. Now, this is. I'll just show you. This is what Resnet looks like as a model. This is where's my classifier gone? Where is my classifier gone? Right. This thing called backbone is this. It's a feature. It creates feature maps. It's a feature recognizer, right? That's what the backbone is. And this is the thing that's been pre-trained on ImageNet, right? So we don't need to do a whole lot for that. We just say this is, and there's different versions of Resnet. This is Resnet 34. It just means it's got 34 layers in it. There's also Resnet 18, which has 18 layers. And there's a couple of different kinds, but this is just a basic Resnet with 34 layers. And this is the thing that finds the features, this backbone. And this part is the classifier. Now, what I'm doing here is I'm freezing the backbone for the first few epochs. So what this will do, it will only train the classifier part. It won't train the backbone for the first like 10 or so epochs. And then once it gets to 10 epochs, it'll unfreeze the backbone and it will start to train the feature recognizer as well as the classifier. Does that make sense? Do you understand what freezing the backbone is?
Yeah.
Yep. Perfect. It's just a way to help train the classifier head, which is an important thing to do. You need to ensure that both parts of the model are trained. This should already be fairly accurate because it has been pre-trained on ImageNet. For Resnet to work, you need to do some transforms. You have to normalize it. These numbers here. It might be good if you ever want to use Resnet. This is what you have to normalize. This is what you have to normalize it with these means and standard deviations, because do you know normalizing? You subtract the mean and divide by the standard deviation.
Yeah.
Yep. So for Resnet to work, this is, you need to use, if you're ever using Resnet, you need to normalize by these values. It needs to be a tensor. You need to change it to, well, it has to be a tensor because we're using PyTorch, and PyTorch doesn't accept arrays and stuff. It only accepts tensors. All these things are just like random horizontal flip, random rotation. That's just introducing a bit of randomness in the data that reduces overfitting. Do you understand what that is?
Yeah.
Like if you introduce stuff like that, it just introduces
If
noise in the data, and it makes it more. It gives it more of a. It means it's just looking for general features. It's not. It's not like it won't get overfit on the training data. If you understand what overfitting is, like it adapts too much to the patterns in the training data,
yeah,
to
the
the point
noise
that it's
too big for
unrealistic.
the
Yeah,
data. Yeah.
yeah. So that's all this is. This is just reducing overfitting. Also resizing. We're resizing all our images to 244 by 244 because that's what ImageNet uses. So that's the thing it's been pre-trained on. So if you're using Resnet, you size everything to 224, and you do this normalization. This is just loading everything. They're using a batch size of 64. It's loading everything into the train loader. This is a very useful thing to have. This, do you know what this image folder command does?
I'm guessing it puts all the images in a folder, but I am not sure.
No, it means if you've got a data set, that is structured.
Okay. So,
I'll see if I can find one of my. Data sets. Yep. So if you've got a data set that's
it,
structured like
okay.
this, so
Mhm.
say it's got a folder named after each of the classes, and in this
Mhm.
folder is a whole lot of images. It will put these all into a tensor, and it will assign the name of the folder.
Labeled. Okay.
Yeah, it will assign the name of the folder as the class. So that's an incredibly useful thing to have. So if you've got a data set that's structured like this, it's this image folder command works really well because it automatically puts all the name of the folder in as a class. This is just, doing the, this is just doing the splitting it into the train and validation sets. Yeah, this is just splitting the data into train and validation sets, and then we put it in a data loader because most of our I actually don't understand like that. That might be a helpful thing to do, to look up what a data loader actually does. I don't have a full understanding of a data loader at this point. I haven't looked it up. That's something I might do at some point. But if you that might be worth for your machine learning knowledge, looking up exactly what a data loader is and how that operates. It's basically the thing that loads the data into the input layer of the network. That's basically what that is. Now this is just going through. Remember, in PyTorch we have to manually do all our back propagation and our stepping function and stuff like that. That's all that's doing. That's training to train one epoch, and it's calculating keeping track of our predictions, what we got correct, and what have you. This is to train it, and this is basically the code here is basically the exact same stuff that's in here. This is just to evaluate it. So this doesn't have all this stuff. It just runs through and it just runs through and does the forward pass and finds classes for everything. Now, there's a number of other things that I used in here. I'll just see if I can. I also used a thing called, I'm not sure where it's recorded. I also used a thing called label smoothing. Oh, yeah, label smoothing. Now, what label smoothing does, generally, have you heard of a thing called one-hot encoding?
Yeah. I mean, I've got an example, if it's okay. A
Yeah.
matrix of 0, 1, 0.
Yep. Yep.
Yeah.
And what that's basically the each label is one hot encoded. So say this is red, green, blue, and yellow. If a thing's green, it'll have a 1 in the green column and 0 in all the other columns. And this is how we do this is how Python handles the labels. So, this means it's green. If it's yellow, then this one will be 1 and this one will be 0. That's one hot encoding. Now, what label smoothing does is label smoothing says, hang on, where it's instead of saying it's 100% green, we're going to say this is to reduce overfitting. Instead of saying it's 100% green, it says, no, we're 90% sure that it's green, but there's a
Okay. So,
chance that it could be
so,
red.
it,
There's a chance that it
so,
could, yep,
so it removes a small portion of the existing value and adds it to the zeros.
yep, yes,
Okay.
that's exactly what it does. And
Okay. Okay.
these will all be equal. So that's like, that's 0, 3, and that'll be 0.03, and that'll be 0.03. And that reduces overfitting. It reduces it because what we're looking at what we're looking at the end, we don't just want to increase the accuracy and have the highest accuracy possible. We also want to decrease the loss. Now, the loss depends on accuracy, but it also depends on confidence scores for each of the predictions. It's still better, even if we get the prediction wrong, if we have a low confidence score for a wrong prediction, it's better than a wrong prediction with a high confidence score. Does that make sense?
Yeah.
We don't want the model to be getting it wrong and being 100% and thinking it got it right. That's, that
Yeah.
makes it less accurate. If we then take it out and train it on data it hasn't seen before, that will make it a lot less accurate if the confidence scores are messed up like that. So, and that's what this does. It evens out, it stops it from becoming overconfident on predictions that are based on the training data. So if this prediction is correct, it won't be as confident, and that's, like I said, it stops it becoming overfit and over reliant on the training data. A lot of this stuff is to avoid overfitting. Now another thing that I've got is weight decay. Now what weight decay does is if you get really big weights, that also means it can easily become, big weights is a sign of it being overfit to training data. It means one part of the map, of one part of a classifier is having a really, really strong effect on other parts of a classifier if we've got really big weights for things. So all weight decay does is decreases it decreases things proportional to the weights. It's part of the optimizer, as you can see. Now the optimizer, yep, the optimizer, as you remember, is weights minus the gradient times the learning rate. Now, what this becomes with this stuff, with weight decay, is the weights equals the learning rate times, I think it's like times the gradient times the weight. So you see, if it's a big weight, this value will be much larger, so it will decrease the weight more. Does that make sense? You there?
Sorry, Sam, what was that? Sorry, I had to step out for a quick second. So.
Oh, that's okay. That's okay. This is weight decay. What weight decay does is it stops the model having really big weights, because if you've got really big weights, that means it is likely to get overfit, because it means one small part of one small part of the algorithm that has really big weights has a disproportional effect on the rest of the prediction. Does that make sense?
Yeah, okay, so basically what it does is to prevent overfitting, it penalizes the large rates, the ones that are
Exactly.
too high.
Yes.
Okay. Yeah.
Perfect. Yep. That's what it does. That's it applies to the optimizer, so that's the maths of it there. It's the optimizer, instead of the weights minus the gradient times the learning rate, it'll be rates minus the learning rate times the gradient times the weight times the weight times the weight times the weight decay. Times weight. Let's call it WD times the weight decay. Great. So yeah, it penalises the weights. You got it in one. Right. So so there are a couple of the features that I've used to improve the accuracy on it. Like I said, the weight decay and the label smoothing. And yeah, we ended up getting this. We ended up getting this one up to. This isn't the
87 was it?
76. This isn't the good one. This isn't another thing that's good to do is
Yeah, it keeps repeating the same thing, so it's
yep,
better to stop the e-post before,
yep,
waste of computation.
yep. But we only save the model if it's better than the last model.
Yeah.
Right. So see these ones are saved because they've been better than the last model. This one wasn't better, so it hasn't saved it. And if there's too many of these, if it doesn't improve for like 4 epochs, then it stops training. That also prevents overfitting. See, this one here is getting a bit overfit. See, we've got our training accuracy is getting more accurate than our validation accuracy, and our training loss is better than our validation loss. This is starting to overfit, and if we keep going, this is going to keep increasing, and this is going to stay the same. It's going to get more and more overfit, and it's not going to do well. It's not going to do well if we put new data in it and try and get it to predict it. I'll try and find the one that I got, because I got one that was up to like 80. I'll try and find that one. Which one is it? Not that one. Not that one. Here we go. Yeah, got this one up to 87. Now, this one is basically just using better data than the one that you were using. I'll explain a bit about the data. This one is using This one's using a thing called REF database. And you see the faces in here. They're a bit better than the faces that are in the data set that you were using, which was the first one that I was training on.
Okay, yeah.
And if you get the major important thing is to get high quality data, is to get data that it can really
Train on,
well
yeah.
adapt to. If you get high quality data, it learns the features better. It learns the features, like with an angry face, for instance, you see the eyes narrow and the mouth tightens and stuff like that. And the better quality data you get, it's going to be able to better, capture that.
Yeah.
And that really increased my accuracy. As soon as I started using this data set, my accuracy went up like 20% from 60 to 80. So that really matters. I'll just quickly, the last thing I'm going to show you is the pipeline that I'm using, because what I'm doing for my image, I don't just want to classify images as I don't just want to classify an image as an emotion. I want it to classify the face as an emotion. And I'll show you an example. The first data set I got, well, not the first one, another data set I got that has more faces in it. This is another data set I got. See how it's sort of zoomed out from a lot
Yeah,
of the faces?
yeah.
This
Yeah,
isn't
you can't
good.
exactly see the faces. They're too
Yeah.
small for the.
So we need to first identify the face and then create a new image with just the face in it and then classify that. And we also needed to get rid of all the stuff like this, which is rubbish, which is, it's good to be able to train it on data sets like this. It's not necessarily going to help the accuracy, but it is going to make the model more generalized, which means it's not going to be overfit on the really good data that you've trained it on.
Mhm.
It's going to be better at looking at random images out in the wild, and and have have a better go at classifying them. Um, it's just going to be more generalized. So what I actually did with this one that got like 80%, 87, I pre-trained it on this data.
Okay, so you can, identify the
I
weird
pre-trained,
images.
yeah, I pre-trained it on this data, and then I fine-tuned it on the good data set. So it has a bit of this generalization in it, and then it's been trained on the really accurate data set. If I didn't do this, it would potentially be even more accurate on the really good data, but it would be unrealistic, and it would be a bit, I would say, a bit overfit. It's too you need it generalized, but you also need really good high quality data for it to learn the features. So it's a bit of a, it's a bit of a
Trade-off.
yeah, it's a bit of a trade-off. I'll just show you my pipeline. Where's my one with the pipeline in it? Not that one. This one. I think, yeah, this is the pipeline. I just used there's a YOLO thing that specializes in detecting faces. YOLO 8 face detection. So I just got that off. I think that gets it off GitHub. Yeah, repo ID. That's the GitHub thing. So it just gets that off GitHub. Runs. This is my image. So it opens the image. This runs this YOLO 8 API on it and draws a bounding box. If you know how to, a big thing that you'll do if you in any object detection, you draw bounding boxes around the object, and it just
Oh,
detects
yeah, sure.
the face. If you need to do anything like that, I can send you this code if you want, or and this is again, this is choose the best face. So say if there's 3 or 4 faces in the image, it looks at both the confidence score for each face and also the area. So it goes for accurate and faces, and it goes for larger faces, and that's how it chooses the best. How it chooses the best face in the image. So because each image we just want one face. This stuff, it just makes sure that the face doesn't go off the page. It just adds some padding at the edge of this is because we're cropping the images, so it adds some padding to the crop, and it also, if it goes off a page, it just brings it back so the crop is still on the page. This is where we process the image. So we run all of these on it, and we do the actual crop. This is the actual where we're actually cropping it. We also delete ones. We delete face images that don't have faces in them. That's somewhere. There's the one thing that deletes images that don't have faces in them. If it doesn't, like, if there's no, if there's nothing in the results, if there's no detected faces, it just deletes the image. I mean, I can, if you want, I can send you this stuff, this code for this, and you can have a look at it. It's quite easy to figure out as you go through it. It's not as complicated as the CNN stuff or the Resnet stuff. And I was just basically going through cropping all the images to make
fine-tuning the data.
Yeah. So what my pipeline is going to look like, to have, when you put a new face in it, the first thing it's going to do is it's going to run this on it. It's going to run this code, and it's going to crop out, and it's going to crop out the face, and then it's going to run, and then it's going to run this Resnet on it. I'm probably going to be using the 86% accurate run. And I'm going to be using this Resnet on it, and it'll guess the emotion of the face. The next stage I'm probably going to try and do after this, probably in the next sprint, is I'm going to be looking at videos, and I'm going to be looking at classifying the emotion in each frame of the video, and then looking at and trying to determine general expressions from the images that are cropped in the video. So say if there's, it's going to be looking at the video like 20 frames and working out like the average emotion in each of the frames. And if it's like, if
there are more sad, it's more than likely she's sad. Okay.
Yeah. That's basically the next stage of where this is going. But how do you feel? Like, I don't know how good a job I did of explaining everything. How do you feel you have a bit of a general understanding of how how convolutional networks and Resnet works?
I think I've got a clear idea on how everything works. It's pretty clean in my mind now.
Nice.
So I can even see how your pipelines are going. I can, it's pretty cool. I get the gist of how everything works.
What I would recommend, if you really want to get into doing, like, in your own time, if you want to get into doing a bit of machine learning, is you could just try making some basic neural networks, or even a basic convolutional network, just on some readily available data. Like, you can find it online. If you look up online, like, how to make a basic neural network, I just looked up like training loop for a PyTorch model, and it'll show you how to make
Yeah,
a
yeah, how to
basic model.
generate a model. Okay.
Yep. Yep. It'll even show you how to download a data set. You can just use, like, there's data sets you can download using PyTorch. There's a PyTorch library that has pre-existing data sets in it. You can use that if you just want some basic data sets, or you can find your own online if you want. But just try enacting some of these. Like I said, if you want to get into like machine learning or whatever, just try enacting some of these simple networks on some commonly available data sets, and see how you go, and just see that you understand everything in them. Try changing some things, look up things like you can change, like weight decay and label smoothing, stuff like that. Experiment a bit with the structure of the network.
Yeah.
um, in this, you could add you could add more You could add more layers. You could add more layers to this if you want. You add another linear layer. You'd have to add a linear layer and a ReLU. Remember, you don't for your last layer for PyTorch. You don't add anything for your last layer. You just have the linear layer. You don't add anything like this, because the optimizer automatically does a softmax on it. Yeah, but like I said, just try experimenting with some of these basic networks. And yeah, that's that basically summarizes what I've done. What I've done with with this network that I'm working on. And yeah, I hope it was, like I said, I hope you have a fairly clear understanding, and I hope you found that was helpful.
Yeah, it is. Yeah.
Yeah, well, it's good. Did you have any questions?
I'm so far no, but once I start to get into it, try out some things, I might get a one or two quick questions. So I'll
Yeah,
just pop by in your chat and ask you if I've got
yeah,
any.
definitely, definitely. Um, I hope you don't mind that it's recorded, because I'm going to show this to some of the other guys in the team.
Yeah, yeah,
Um,
that's okay.
yep. Also probably going to put this forward as one of my contributions.
Yeah,
So yeah. Well, thanks for taking the time to come through, and are you just doing AI, or are you doing like front end or back end or something as well?
no, no, I'm doing backend. So that's my main
Okay.
task. I've
Oh,
I've
good.
already done my sprint task. I've done a few leadership contributions in there.
Oh, lovely.
Yeah, so
Lovely.
I'm just trying to do what I can in
All
AI.
right.
I just
So
want to
I
pop up.
don't need to worry too much about finding you work to do. That's
Yeah,
yeah, that's good. That's very
yeah.
good, because most of, like, part of the problem is also, if most of the stuff like this machine learning stuff, I think the best thing you're going to get from it is just looking through what I've done, and learning a bit, and maybe, like I said, also doing some tasks like you were doing with the convolutional neural net, just having a play around with it and understanding it, and seeing if you can. Did any of the stuff that you did improve the accuracy of it?
Yeah, it initially didn't. I tried to increase the epochs, and it
Yep.
started to go downhill once it started to hit that 13 and later on models. So what I did is, once it started to not react to the model and there is no improvement, what you did, I decided that it's better to just stop the epochs once
Yes.
there's no improvement and all.
Yep.
And I've also tried to meddle around with the different values. And yeah, as I try different things, it just went good.
Yep. The main thing you've got to watch is overfitting. Like, look at this. This model's actually doing really good. See the train loss here, and the train accuracy. The validation is better than the train set. That's good. You want them to be sort of sitting around you want these to be about equal. You want the training accuracy and loss to be about equal to the validation accuracy and loss. If this is a lot less, then it means if this is worse than the validation stuff, it means it's underfitting and you need to train it more, and that will help the validation accuracy. If this is better, then that's really bad. That's overfitting. And if you look where it stops saving it, where this stops improving, this
Mhm.
this starts overfitting. See, this training accuracy is starting to become better than the validation accuracy, and this gets worse. And what this means is if this is a lot higher than this, the model is going to perform even worse when you take it out and try and
On a real life data.
predict other data, because it's going to be overconfident with the wrong predictions it makes, because it's too because it's too fit on the training data. So you want this stuff to be, you don't want this to be less than this. You want this to be about equal with this. That means
Yeah.
you've got that means your model's performing well. And you want your loss, like this loss still isn't great. Like a good loss is like, below 5%. This is, this is a strong model. This is, performing well, but it's still not, still not ideal. To get higher accuracy, I'd really need, better data, which isn't necessarily out there. There's one out there called EffectNet, which I was trying to get, but might actually stop the recording because I've taken you through everything. So I'll stop the recording. And like I said, I hope this is useful for people. It's not what I wanted. How do I stop the recording?
Yeah.
All right.